So thank you. Yep. Today I'm going to be talking about considerations of where encrypted DNS will actually push operators in terms of new things that they have to deal with. So as we heard yesterday, DNS protocol is evolving. We have two new standards. I'm going to use the acronym DOT for DNS over TLS and DO for DNS over HTTPS. One thing I want to call out is that these efforts came from really quite different origins. DOT, work started on that about 4 or 5 years ago. It's been a standard for 2 years, and it came out of the DPRIVE working group. And one of the goals with this was that DNS community recognised they had to encrypt DNS, but they wanted to do it with the minimum delta on the existing infrastructure. So one of the goals here was, please don't upset the camel. It's already having a hard time. The camel will get sad, Bert will get sad, everybody will get sad. Let's not go there. So that was some of the motivation behind DOT. Whereas DO is quite different. It's come about really mainly in the last 18 months. It's been largely driven, not exclusively, but largely driven by the browser community. And it has a whole different set of use cases. One of them that's called out in the specification is that it's designed for web applications to be able to access DNS via existing APIs. And at the moment, we're really not sure what the full spectrum of use cases for DO will be. So that's one of the open questions here. Whoops. So, some fundamental things that encryption will change. Well, of course, it ticks the boxes of defeating passive surveillance. As a nice side effect, it provides data integrity on the transport, so you can't inject spoof responses into encrypted streams. Also, it has the option to authenticate the server if the client can be configured with the correct authentication information, so this is all nice. However, as with many other contexts where encryption has been deployed or increased, it really does provide new operational challenges for operators. And in fact, the IETF has directly recognised this. In the lieu of the debate over TLS 1.3 and the pushback from some operators on that, the IETF wrote an RFC, which is called The Effects of Pervasive Encryption on Operators. Now, at the time, it was kind of largely targeted at the web server community, but the reality now is DNS operators need to take notice of this and start reading it because it's going to affect DNS operations in a similar way. One of the big things that encryption on the wire does is it changes the focus. So there's no longer the argument that, well, it's in clear text, it doesn't matter. The argument then becomes, what really matters is where your queries go. What is the resolver choice? Because that actually becomes one of the single biggest potential threat vectors in the new model. Now, there are many actors in this world of have the desire for encryption. So there are end users, application developers, organizations. Today, I'm going to try and cover the things that are of the most concern to resolver operators and to network operators. So I'll focus here on those concerns. Oliver went over this yesterday. There's various open source implementations of both DO and DOT. I will call out Android Pie as a DOT implementation, where Android Pie now does opportunistic DOT by default. In other words, it will take the IP addresses from DHCP and it will actively probe them on port 853. And if it finds service, it will use that in preference to doing UDP. System D, love it or loathe it, is going in roughly the same direction. And I'll also mention Stubby, which is probably the most widely used desktop client for DOT, beg your pardon. And for DO, it's a little bit of a different pitch there. It's really the browsers where we're seeing the very early implementation and deployment. Again, as we heard yesterday, there are a number of cloud-based services for both of these. Both Quad9 and Cloudflare now do both DO and DOT. So there's a number of choices there. Okay. But one thing we are seeing on the deployment side is because we now have devices like Android Pie that are actively probing port 853, we are seeing operators being increasingly interested in deploying DOT in particular on their networks to take advantage of that change in how end-user devices are actually doing DNS. Before I go too far down this road, I want to call out a couple of differences between the protocols at the specification level. One important one is discovery. Today, there is no mechanism to discover a DO server dynamically. To do DOE, you have to have a URI, which can't today be bootstrapped from an IP address. And that's in contrast to this opportunistic method of DOT, where you can just probe on port 853. So there are some proposals in the works, and I'll talk about more of those later. But that's a distinction in today's world. The other big distinction is with the connection model. Now, DOT, obviously, you're doing dedicated connections where all you're doing is DNS queries. There's a similar model for DOE where you have HTTP connections where all you do is send DOE queries over that connection. And because they look like HTTP and because they're on port 443, they're much harder to block than the DOE connections. But with DOE, there's a second model, and that's a mixed connection mode. And what that means is an application could potentially already have an HTTP connection open to an endpoint. And if through some discovery it knew the endpoint also did DOE, then it can start sending its DOE queries on that same connection, completely mixed in with existing HTTP requests. Now, this is an interesting model. There's been some arguments to say this has the potential to increase user privacy. For example, I have a tab open in my browser to my bank. I know my bank does DOE. I can send my DNS queries to my bank, and therefore I'm not exposing them to a third-party DNS provider. And my bank already knows all the content I'm going to look up there. The thing is, what that also means is that in that context, it becomes impossible to block just your DNS queries because they are completely mixed in with your HTTP traffic. To block them, you'd have to block the entire HTTP endpoint. So this is an interesting case of where you have a classic conflict between something that could potentially provide improved user privacy, but at the same time can cause operational problems through obfuscation of traffic. The last thing I want to call out is that HTTP potentially changes the privacy model. If you have an end-user device doing DOT from a system resolver, for example, you see a stream of queries from one device for all the DNS lookups happening. If, however, you have multiple applications on an end device, all, for example, doing DOE, each stream is going to include HTTP headers on each request it does, and each stream is going to have a unique user agent, language identifier, etc. And that means that each of those streams can be traced back to the individual application that originates the queries. So it adds a whole another level of granularity on being able to profile the DNS queries coming out of an end-user device. So a whole new set of privacy concerns there. So what's happening with DOE in browsers? Well, one thing to just touch on first is why are browser vendors going down this route? There's been various blogs about it. That's a link to one by Mozilla. And it comes down to a number of things, including the fact that the browsers are saying, well, operating systems are so slow to evolve their DNS libraries. We saw it with DNSSEC. We're still seeing it with DOT and DOE, and they're not willing to wait for the third parties to do the work in offering these services. They want to have a selling point. They want to say, we're a privacy-preserving browser. We care about the privacy of our users. Look, we do DOE. They also see opportunities to increase the user experience, which is obviously the holy grail for a browser, including things like latency. And they're just starting to tap into how they might do this with DOE. Who exactly is doing what? Well, Firefox have been leading the way. They've had DOE available since Firefox 61, so it's at least 6 months. It's there, but it's not enabled by default today. But they have been doing some very interesting experiments in their Firefox Nightly build, and I'll talk about that in a moment. Chrome also has a DOE implementation. Now, it's not exposed today with the user configuration, and it hasn't really been talked about. But a couple of weeks ago, a PR got put in to actually enable a user config option in Chrome, so that's certainly on the way. One thing to briefly mention is that when you look at things like blogs about this and even some of the config settings, the browser folks use the term secure DNS to describe this setting. Now, they're doing that by extension of how you talk about HTTP and HTTPS, obviously. I personally really dislike this term because I think there's potential for confusion because using DOE has absolutely nothing to do with DNSSEC, and I think there's room for confusion there, and I prefer to see a different term used personally. One other thing to mention here is that there's scope for rapid evolution in how DOE is used, and that's because browsers control the client. They can put new features in, they can put experimental features in a way that just simply isn't possible in the evolution of an operating system level library. What precisely have Firefox been doing? They first announced some plans back in May to do an experiment, and this the blog post that they announced at the time had two things that really caught people's attention. One is that they said that they wanted to turn DOE on by default. And the other is that they coined a brand new phrase, TRR, Trusted Recursive Resolver. And they stated that because they'd chosen Cloudflare, hi Oliver, as their TRR, and Cloudflare had a really nice privacy policy, that in some circumstances, Firefox could ignore the network-provided resolver and go straight to Cloudflare. So they went ahead and they did their experiment, and they published the results in August. And they did it by sending queries simultaneously to the system resolver and to Cloudflare. When they published the blog, where they described the results, what I found interesting is that they said the number one question they were trying to answer that experiment was whether the use of a cloud service performed well enough to replace traditional DNS. So it wasn't about ironing out protocol details, it was about this much, much bigger question. The summary of the results was that they concluded there was a 6 millisecond overhead in doing DOE, and that for them that was acceptable because you got encryption. In the moving forward section of this blog post, they stated that they are interested in building a large ecosystem of trusted DOE providers. So they're clearly going down this path of genuinely considering shifting to cloud-based resolvers as a default. And they've actually progressed this even further. They've taken the experiment from Firefox Nightly, and it's now going to be run in Firefox Beta. So coming back to one of my earlier statements, what this means is, as a community, we really have to come back and think about what happens about the resolver choice on an end-user device. And this choice can happen in multiple places. One of the places this happens, the main place today, is obviously in the system resolver, which uses DHCP in most cases. Now, in order to do DOE or authenticated dot, the client needs extra information which isn't available today. It needs a name or a URI. And at the last IETF, there were proposals to extend DHCP to include this information. However, what happened there was that the IETF said, we do not recognise DHCP as a secure method to deliver this information. So if the delivery of information isn't secure, it doesn't provide value in creating a secure DOE or dot connection. So we don't think this is worth pursuing as the way to provide this information to clients. The interesting thing is, when I talk about this, and every single operator I talk to, they say, I do DHCP today. I intend to do it for the foreseeable future. I don't want another mechanism. I want a solution in DHCP. So again, we have another fundamental conflict where the standards body and the operators want different solutions. Because DHCP isn't being considered as a secure delivery mechanism, there's been some other proposals. They're mainly about in-band. For example, a client could query a resolver over clear text or over opportunistic dot and discover what services the resolver offers and then choose what to do. Unfortunately, none of the ones proposed today are secure either for this in-band mechanism. So we're at a point where discovery is a missing link. We really need work on this problem. The second place where the resolver choice gets made is obviously in the application. There's no precedent for this, so we don't know where this will go, and I'll come back to this later. The third place that I just want to raise is we're getting close to a state where organisations have policies about DNS. I mean, one of the things that drove the adoption of DNSSEC was when the US government mandated it for all their government zones. Could we see something similar from a government or a banking institution that starts requiring encrypted DNS? And lastly, there's a question of privacy-aware users or communities of users. And these are the people where you actually have to go back to basics and think about what's the threat model here? What are we actually thinking about? And it becomes important to try to categorize trusted and untrusted networks. And this isn't something where we have a nice, clear definition we can reference, but it's where the privacy policy of the network comes into play. one example, and I think Bert brought this up at the mic yesterday, is that in the US, many users see their ISP as the threat because ISPs are trying to monetize DNS data because of the lack of net neutrality. They can do that. Whereas in Europe, GDPR provides really pretty solid protections around what ISPs can do. And they're actually probably one of your best options in terms of maintaining user privacy. So we really come down to a question of needing transparency and accountability from operators to build trust to help us discriminate the trust model and untrusted and trusted networks. So here I'll just touch on a couple of things to do with the impact of encrypting DNS within networks. So this is your network operator, and I offer either DOT or DOE on my own resolver. What does that change about the way I run my network? So there's all the obvious things. You're switching from UDP to a session-based protocol. There are performance concerns, both on the client and the server side. There's concerns around DOS because attack vectors will shift. Some are nullified with encrypted technologies, some are amplified. And also you're potentially operating your DNS service over multiple transports, and this can add complexity. Some other new things that people need to think about as well, which are the kind of things that are raised in the RFC on this, is that you're probably going to have to revisit your monitoring and your troubleshooting practices because the luxury of passive monitoring is gone. You can't just switch on TCP dump and see an encrypted stream anymore. The other thing is that you'll probably start getting more focus on your data handling policies. DNS is PII, and once it's not encrypted on the wire, you have to start thinking about what you're doing in terms of your data retention and your data anonymization. And there is another draft linked through that best practices link where we try and describe what operators should be thinking about when they start offering encrypted services. Here I want to talk about the potential impact for TRRs. Now, we don't even know for sure this is going to happen. Firefox now are not committing. They've kind of backed off a little bit. They've been asked repeatedly what their stance is, and the answer is, we haven't decided yet. And the problem here is this leaves the DNS community in limbo, waiting for a decision from browser vendors for something that could potentially be a major impact on DNS infrastructure. And we're just sat waiting. So if they did go down this route, what are the things that this would change? So one of the big things it would change is the current trust model for using a DNS resolver. For better or worse today, the trust model is, by choosing to log onto a network, I'm effectively choosing to use the DHCP provided resolvers, and that's the way it's historically been. The new trust model could be, I install a browser and buried somewhere in the T's or C's is a little thing that says, by the way, we're going to send your DNS queries to whatever browser we select by default. I've been asked a very interesting question by a government official at a talk I gave a few weeks ago, which was, hang on, under GDPR, users are required to give informed consent if their data is to be taken outside of Europe. Do you really think users can do that when they don't even understand what DNS is and they don't understand what PII is in there? And possibly also, if the provider of the service can't or won't declare where their data is stored. Hi, Oliver. One of the other things that this raises as a question is, what if this leads to a potential centralization of DNS services? What if browsers start coming with predefined drop-down lists of cloud providers that you can use? Now, they're probably not going to block you from configuring one, but most users won't do that. What's interesting here, this is being led by Mozilla. Mozilla have a core principle to be against the centralization of the internet. They do so many other good things in their browsers, and yet they seem to be going down this path. Can you imagine a world where, just like browsers approve lists of CAs, they're going to approve lists of cloud-based DNS providers? It's possible. We know that where browsers go, applications go, lazy router vendors go, who knows where this could lead? What about if certain governments start saying, if you want to sell your app in our app store, you have to use our TRR? There's a whole range of questions that come up, including questions about operator neutrality. If you're a CDN, do you have a conflict of interest to serve a content provided by a rival CDN if you're a chosen DOE provider? Hi, Oliver. Back to the issue for operators that they have to tackle. One of the things that will happen if somebody in your network chooses to use a TRR that's outside it is it will break split horizon DNS if you're using it. Now, this can happen today if they use 888, but you can see that. With encrypted traffic, you just won't be able to. So what that means is that traffic could potentially bypass your local monitoring and your security policies. And this is a really big concern for many operators because some actually have legal and regulatory requirements on the control of the DNS. And that's a historical thing because they've been able to do it because DNS wasn't encrypted. And that is something that will have to shift. Others are being a bit more aggressive and saying, hang on, I'm just going to block this stuff or proxy it, my network, my rules. So there's a range of reaction from operators here. One thing I would appeal and say that if operators can by default start offering services which have equivalent privacy policies to the cloud-based services, then it diffuses the justification for saying any application should go outside the network. And hopefully will stop a centralization to those few providers. What's next for DOE? Just a few things that could be on the horizon, depending on what catches the browser vendor's eyes. So, for sure, JSON is coming. I think within the next year, there will be a media format for JSON within DOE. Absolutely, they're going to take advantage of server push. Now, this actually lends itself quite naturally and quite nicely to DNS because, you could potentially reduce latency if you can solve the problems of being sure that those pushed answers have the right security perimeter and don't end up in caches used system-wide. Also, the browsers have only implemented the dedicated connection model, not the mixed one. So who knows where that could take us in terms of what that will actually mean in practice. Again, most of this is being driven by the browser community. So, final slide, what to do. The appeal is, if you're an operator, think about running a DOT server. There are devices out there probing your network who would like to do opportunistic DOT, so please support them. Also think about running your own DOE server. That at least gives users the choice to use a server within a trusted network rather than having to go to a cloud provider. Please review your privacy policy and your practices. Take a look at the BCP and think about what you're doing today. Also, this stuff is moving really, really fast. We don't know what could happen in the next release of any of these browsers. So my biggest piece of advice, if you want to know what's going on, don't blink. With that, thank you very much.
Should I let Oliver go first?
Probably.
Hi, Dale. The one thing that I think you actually kind of glossed over in perhaps a much more positive way even than it should have been is the server push idea.
Yep.
I think that the DNS community does not really appreciate what a sea change this could represent for the operational architecture of the internet.
Yep.
It has significant issues to solve. As you mentioned, the security, can we trust records that are being pushed? It is driven by the web community, but it can really have a huge effect on the operational impact, especially of companies that are providing services through the DNS, like load balancing or geo mapping and so on. I'm not sure how else to put it because I don't have the solutions to it either, other than like I see a giant steamship that's heading in this direction, and that the DNS community seems to not be really paying sufficient attention to just what it implies for their architectures of their CDNs and so on. So.
I think that's true. I think the DNS community is beginning to be aware of it, but I think there's not a huge amount of concrete proposals. I mean, we haven't seen... one of my fears is we won't see standards or clarification of this. It will just start happening in browsers. So that's a big concern. And the thing is, there's nothing in the spec that precludes that happening, right? So, yeah, so we need to keep an eye on that. Jim?
Hi, Sarah. Great talk, as always. I think there's one thing you might have missed a little bit here in this overall scheme is that we're talking about this, obviously you've got great focus here on the privacy concerns around this stuff, but there's also going to be a big problem, I think, in enterprise networks and things of that nature, because they're relying on DNS managed services to do things like block access to particular websites and other kind of resources and stuff of that nature. You did talk about this of having an impact on local policy.
Yeah.
But I think it's going to be very interesting for the providers of those services how they're going to try and solve that problem and what enterprises are going to do about it, because I think this is a big concern. And the other problem is because this is going to bypass even all the conventional control mechanisms like how you deploy and implement your IT infrastructure. Someone's going to download the latest version of a browser, or they're going to get the latest client on an app for the phone, and this stuff will be there. It will be switched on, and the IT managers have got no way to control the police that.
Yep. I mean, I think today we have very exceptional cases where somebody might choose to use Tor, or there are some ways of encrypting it. The shift here is that this becomes the norm if the applications are doing it, and puts it at a completely different scale.
And it's going to happen essentially by stealth.
Very possibly, yeah. Or we don't know how it's going to happen.
Yeah.
Yeah. Ralph, or... See?
Okay, a couple of remarks also.
Just a quick interrupt. Oliver wants to wait to the very end.
Yeah.
Yep.
So...
Should we... Okay, yep.
Okay, so DNS 6.4 probably also will be a problem, and the other thing that will be a problem is that there are regulations in lots of countries of stuff that you block, and usually what governments or regulators have done these days, they use DNS because it was an easy mechanism.
Yep.
The providers get it and they'll get a list and then it's blocked. With this, it's kind of, it's not working, and the question is what will the regulators then do, or the governments to actually enforce that?
Yeah, so it's a challenge not just for the operators.
And one of my nightmares with this is, and because I started out my professional career doing support as for an ISP, and the support calls will be just staggering because my browser can't get there, my mail program can get there, and my Android phone does something totally different. I mean, it's kind of it will be a nightmare. So it would be really good if we could get away of the idea doing it per app and doing it rather sort of per OS or per some larger entity.
Yeah. So I gave a talk at the ICANN DNS Symposium a few months ago, doing this but from the user perspective, which is suddenly my DNS management and infrastructure on my device is fragmented. I have 10 different places that send queries to 10 different resolvers potentially, and that's going to be a shift as well. Yeah, agreed. Oliver?
Hi, Sarah.
Hi, Oliver.
Very good talk. Some good things in there. There's a fair amount of FUD. You talk about changes, and changes are sometimes good and sometimes bad, and sometimes we should look at them as opportunities. I think this is really exciting technologies that are being done, and I remember how hard you pushed the DNS community in the beginning to make DOT possible, and if it wasn't for you creating this monster, this would never have happened. Yeah. So yes, I think this is a very good, and there are going to be gazillion policy questions that have to be answered, and if we look at the EU, it is an island of calmness and goodness. Then there is the rest of the world, and Firefox, if I can put words in their mouth, is they're trying to improve the internet experience for everybody, not just the privileged few. So
I accept that, and I can see, I hope I did try to call out some of the good things that they're doing. My concern here is the lack of connection between the browser community and the DNS community here. So things I don't see Mozilla doing is developing system resolver clients to do DOE. They're leaving that, which I would like to see, because they're only protecting the browser users, not everybody. They didn't connect with the implementers of DNS open source software to potentially fund them to implement DOE. That would have been a really nice thing. And I would like it if they were being more transparent about their rollout plans. So it's the disconnect between the communities that concerns me. And my big worry is that this becomes an arms race, because one day a browser turns this on by default, and the next day operators just start blocking it. And that is not good for user privacy in the long term. So I would like to see a much more coordinated effort between the two to agree how this stuff should evolve.
That is a really hard discussion to get going, and I know that the Mozilla community, based on their mailing list, is really fragmented in how to go forward on it. So I think that is part of the problem. You can't get a clear statement out of them, is because they are arguing internally so heavily, and also it becomes a part of the geographical debate where certain parts of the think that what they have in place is good, and then the other parts of the world are clamoring for something better. And yes, as of the questions you were throwing my way by waving, yes, we are just trying to make it available. We do exactly what we say in our policy about the data sovereignty storage issue. That there will be some statements about that at some point, but I'm not at the pay grade that can answer that.
But also the early adopters also often get a hard time because they're evolving and processing, which I think is
well, the first question that we did with Mozilla was to answer the question, is this viable? From performance reason, and we can argue about the 6 milliseconds, or we can look at the back tail where it improves a lot. So yes, it will get better. Will it get used? I don't know, but it's going to be interesting next few years, and you should look at this as an opportunity, not as a threat. And this is getting rid of UDP is one of my future goals.
I mean, I absolutely want this privacy to happen. The question is, let's have it happen in a constructive way that doesn't scare operators into blocking it.
Operators want to get rid of DNS operations in many parts of the world. They don't want to do it. The day we announced 1111, we got multiple calls from ISP saying, can we switch to you in our DHCP announcements?
But I've also spoken at conferences where I get people like, I don't know, BT or Vodafone saying that we can't go down this route. We just can't because of legal and regulatory requirements.
Okay.
So I think one of the problems is there's such a mixed bag. They're absolutely extremes in terms of what these operators want to do. And this raises questions at both extremes.
Yes, and then there is the operators may not do the blocks. They may be enforced on the transit providers.
Yeah.
So yes.
So
it's not just the DNS operators. It's a big global discussion.
Absolutely. And that's, I guess, what I'm trying to do is just make people aware of what's going on to start those discussions. Do I still have time?
Yeah. Peter Kortinik. Thank you, Sarah, for that very inspiring talk. I'm wondering why you've been so optimistic about this. I think this has the potential to mark the victory of the web over the internet. And there's no less at stake than the uniqueness of the namespace. And I also doubt very much that this is about privacy or technology. It's about governance. And the question that you raised, I guess it was on slide 14 there, the concentration of this. If you think this a bit further, there's an odd chance that the club of providers of these services is finally determining what is part of the namespace and what is not. And while some people might consider that a feature, I think that's a big risk for this technical community, but on the broader sense for the DNS.
Yeah, I mean.
So if you do this, we don't need any root zone anymore.
I think there are huge questions about where this resolverless DNS context-based resolution will go, and we just don't have any answers at the moment. So I could be scarier in my next talk if you want me to. There's
one tweet. Okay. All right. Then everyone, please tweet out that it's an embarrassment that none of the server provider community is even here. We are complaining on their behalf about DNS over HTTPS. So please, next time round, service providers show up and care. Thank you.
Okay. Thank you.
Our next presenter is Giovanni from SIDN.
All right, so good morning, everybody. So this is work we've been doing together at SIDN with John in USC and ISI. and Ricardo, University of Passo Fundo. We have also Marco here and Moritz, co-authors of the paper. They're somewhere here. Yeah. So this is a paper that's going to appear in the next IMC conference, I think in 2 weeks' time. You can download its full PDF, it's open. And, you know, we all know that denial of service attacks are on the rise on DNS. They're getting bigger, they're getting cheaper, and they're happening more often now. The biggest we have seen so far it has been 1.7 terabits per second, and on DNS specifically has been 1.2 terabits per second. There was against Dyn. And if you look at the outcomes of different denial of service attacks against DNS infrastructure, here I have 2 examples. There was one example, the roots DNS attack until November 2015. There were no reports from the part of the users during this denial of service attacks, even though some of the root letters had some problems. And Dyn, another DNS provider, they had a bigger DDoS, and a lot of people complained. And one of the things we wanted to investigate in this paper was like, well, we have 2 large DDoS attacks. They have very different outcomes. So one of the question is why? And we all know there are pretty much 3 parts of DNS, like the user, a resolver in between, an authoritative server. And those are 2 very different actors who run them, and they have like different interests. I name a couple of them here. And pretty much the resolver is like the middleman in between a user and authoritative. And then you go for the queries, you get an answer eventually. And for resilience now, each side has deployed many different features like anycast, load balancers, multiple name servers on the authoritative side. On the resolver side, you see a lot of cloud providers now having anycast. Caching, of course, is one of the things. Retries, multiple resolvers. And what happens when the authoritative goes down or has some connectivity problems? And what we wanted to know is like how clients can actually get affected when this happens, and how much will resolvers help in the case of unavailability, or at least a certain extent from the authoritatives where it's marked there. Because there has been work for a long time in resiliency on the resolver layer. So the way we evaluate DNS resilience is in 3 parts. First, we evaluate under normal operations, so to have a feeling how much the resolvers are responding to that. And then we verify that in production. And then we emulate some denial of service attacks in the wild to observe user experience. So what we did, we registered a new domain that nobody has used on our own. We set up 2 authoritative name servers and run them on EC2. We use RIPE Atlas as vantage points and their local resolvers. So they're like 10,000 probes, but they have like usually more than 1 resolver. So we have 15,000 vantage points. And each probe, I configure them to send a unique query so they don't interfere with each other, which is like probe ID.cachetest.nl, and for a quad A record. And in the quad A, I encode a bunch of stuff, including a serial number and the answer that allows me to tell later when I get an answer if the value was answered from the cache or from the authoritative. Because what I do, I increment every 10 minutes the values, the changes on the files every 10 minutes, and increment the serial value. So when I get an answer, I know what's in the zone file, I know what is the answer that the client got, and I can tell if it was on the zone or not. And we have done that with a bunch of different TTLs because different people run different TTLs. I had a discussion yesterday quickly with Dwayne here. So we're going to be looking at the TTLs because pretty much it's the authoritatives to tell what is the TTL, and the resolvers, which are different actors, use that value to cache the records. That's the maximum value they should cache. So let's measure first caching in the wild. We do not control, we control the authoritative servers and the clients. We do not control recursives. As we talked this morning, it's a very complex infrastructure that may be multiple layers in between. And with the RIPE Atlas, we have no idea actually how big that is. But anyway, we're going to have an idea how much caching works in the wild. And TTL is the metric that allows to set the upper limit for how long a record should be cached by recursives. And that's a figure. So what we see here is on the y-axis is the number of queries, and on the x-axis is the different measurements that we run, the experiments. And we run with the different TTL configurations, and we have probe for 1 or 2 hours, depending on the experiment, every 20 minutes. So what matters in this graph that A the blue color, AA, is very good. This is like when the queries were answered by the authoritative, and they should have been at that time because the TTL should have been expired. The green is also good. The only thing that's not good here is like the yellow one. The yellow one was like, it was answered by the authoritative, but theory could have been answered by the cache. And so, what this graph shows, like roughly independent of the TTL, we see like cache behaves as expected, as you would expect by setting your TTL 70% of the time. If you're not popular domain, so not so good news. You have like 30% of cache miss, which in theory it could have been cached, but it was not. So just give an idea how cache behaves in the wild. And we went to investigate later why actually this happens in the wild. And a bunch of things like caches are very complex. I mean, this resolver infrastructure is extremely complex. Pretty much a lot of people are using Anycast. They have different capacities. Caches can be flushed. They're very complex. They have like different levels of fragmentation. And you look into the answers that were not answered by a cache or cache misses. So roughly half of them were coming from Google. It will look at the right path. So what was the less recursive in that? Because of Anycast, and there's a report from Google on like fragmentation and stuff. But yeah, so our hypothesis, it's that like, these caches are very complex, and our domain was not popular, nobody used it, so that doesn't help either. So this is kind of a lower bound result. All right, so in our setup with our test domain, but using real vantage points from RIPE, we saw like 70% of the queries were cached as expected, and then we went to validate that on .NL in the roots. I don't show here the roots results, but you can check in the paper. We show .NL. And what we have done is we just look into the time in between queries from the same resolver, meaning IP addresses we see on the authoritative name side, server side, and we compare that for the domains of our name servers that we host, and that's a TTL of 1 hour, and that's the number of queries to get, roughly 300,000. And what we see is the CDF here that roughly 28% of the resolvers would not respect the 1 hour TTL of our authoritative name servers that we run. And that shows that in production zone, we see pretty much what I have observed in our domain, like roughly 30% of the people would not respect the TTL, but 70% would cache as we would expect, which is a good result. So that just confirms that. But the interesting part of the paper is the next one. Like we know now how it works in the wild. We can start to emulate DDoS attacks and see how caching would protect users. That's the entire goal of the paper. So we run a similar setup as the other one before. We emulate DDoS attacks by dropping incoming packets on our authoritative name servers. And I mean the test name servers that I ran on Wizenbind on EC2. And the question I wanted to know was like how much caches protect the users, and to understand why some attacks have more impact than others. And I'm gonna focus on the key experiments. There are way more experiments in the paper in a technical report. Scenario A. Let's start with this one. Imagine that your name servers are attacked, your authoritative name servers, and they all become unavailable. That's the worst nightmare for authoritative operator. Only cache pretty much will be able to save your clients. And in this scenario, in particular, I have set the TTL values for 1 hour, and a probe every 10 minutes. So we start with the measurement at minute 10. I switch off the name servers. They will not answer anymore, and I drop all the packets, pretty much. And what we show here, I don't think it's going to be hard to point from here. But in the y-axis, you see the number of answers. In the x-axis, you see a time series. Since we probe every 10 minutes, you see these different colors. And you see an arrow going down before 10, and that's when the DDoS starts. So before that, you see like a lot of people get OK cures, they get an answer because the servers are up and running, everything is fine. When the servers go down, you see like the color blue, that's the one getting the answers. It starts to go a little down. And it gets worse as time passes. So from 0 until 60, like that's when caching is actually answered. People could only get answers on that period if it were answers by cache because the authoritatives are not available. And you see that in that phase, you have 35 to 70% of people are being served from cache. And it gets worse, it gets closer to when the time of the TTL would expire. at the time of 60s, as you can see there. And after cache expired, in theory, they could not get an answer, right? But there is this draft which is very interesting. It's being controversial in ATF. Some people are actually getting an answer. I forgot the right numbers, but 0.2% of the clients were actually serving stale. Pretty much, serve stale states that if you can't reach the authoritatives, serve your clients to the last answer that you knew. And that's been deployed, I think, by Google. I think it's deploying, I'm finding the paper, and I think OpenDNS, so some of them. So I have the numbers in the paper, maybe I want to have a look. Anyway, so then we move to scenario B. Scenario B is the one that we also have a complete failure, but instead at doing that at time equals to 10, where the caches were more fresh, we moved to a little further, around 60 minutes, and that just changes how fresh the cache was from the start of the measurement. Since the TTL here is 1 hour, the caches are about to expire, in theory. And when the arrow goes down at 60, you see that the color blue starts to drop way quicker. And the reason is because the caches on the client, the resolvers, were already about to expire. And so people getting the right answers, they decrease way faster. So cache, in this case, become much less effective at times out. It's the timeouts near the attack. And fragmented cache surprisingly helps some because they fill up later. It's also in the paper, the details. All right, so let's move to another scenario. I mean, complete the DOS again, but let's evaluate how the TTL actually impacts how people get an answer. So in this measurement here, I think it's scenario C, we have, again, TTL, we have like failure at 60 minutes, but instead of having a TTL of 1 hour, we have half an hour. And the DDoS starts at 60. And what do we see? That's the shorter the TTL, of course, the caches are going to maintain information for shorter periods, and less users get served because the caches expire faster. So that brings back to the thing, like ops, people have to choose wisely the TTLs of your records, because the shorter you have, you're limiting how long it's going to be in the cache of the resolvers and protect the users in the case of unavailability of your own authoritatives. So caching is partially successful during the DOS. You cannot expect protection for your clients for a period of time as long as the TTL, because it depends on the state of the cache. Serving stale content provides less resort for a doomsday scenario. It's not widespread yet, but some people are already doing. And TTL of the records, the shorter you set them, the less you protect your users during complete DDoS. But not all DDoS leads to a complete failure of the authoritatives. Actually, in fact, most of them lead to the partial failure, like the roots, for example. It's like in a case that part of the queries get answered. So the question that we also went to simulate those attacks, and we wanted to understand how much that would protect the users. So this is experiment E. What I do here, I have a TTL half an hour, and I drop 50% of the packet. And for our surprise, if you have like a DDoS that actually, in this case, leads to 50% of our queries being dropped, users barely noticed. And that I found fascinating. Most clients were getting an answer because just try again. What happened, it took a little longer. You can actually see the graph below. The green line shows the round trip time, the latency, for them to get an answer. So you see a small increase, but pretty much everybody gets an answer. And I think that's very good engineering from the DNS developers, so kudos for them. This is even more surprising, this one to me. You drop 90%, you have a DDoS that are causing 90% of your packets being dropped. You cannot answer 90% of your queries in a TTL or half an hour. And in this case, the DDoS starts at T equals to 60 minutes. That's when I start dropping 90% of my packets. And the blue color again show the number of clients getting an answer when 90% of the people are getting, of the queries are not being answered. And even in the circumstances of 90% of the queries being dropped at the authoritative, with a TTL of half an hour, 60% of the clients still get an answer. That's pretty much good. That's great engineering. Of course, the price they pay, it's like the RTT goes a little higher, as you can see there in the green line, for the mean value. The other lines are the quartiles. But this is pretty much good engineering. So, and we did another experiment. It's also 90% success DDoS, meaning that we're dropping 90% of the queries arriving. And we have a TTL of 1 minute in the records that they're asking. And what does that mean? Since we probe every 10 minutes, if you have a TTL of 1 minute, that means that in between, next time you measure, you're probing again, the record should already been expired because the time in between measurements is 10 minutes, the cache was only 1 minute. So pretty much you have no caching in the scenario. So that was the idea of this measurement, disable caching by the TTL. And what we see is that when you drop 90% of the packets come into your authoritative and the records have a very short TTL, you see like 27% of the clients still get an answer. And that's pretty good. And we went to investigate why this is happening. And I think it was a known phenomenon, but nobody actually saw it that way. Resolvers, they pretty much would hammer the hell out of the authoritatives until they get an answer. Because they'll be doing their job. So in this time series here, I'm looking at the number of queries arriving at my authoritative servers for that particular measurement, and at 60, it's when the DDoS attacks starts. So I'm collecting everything that arrives. So you see that before that we had less than, let's say, 20,000 queries every 10 minutes, and after that it goes above 150,000. That's because the recursives start to try, okay, I cannot get an answer, I'll try again, and they'll be on trying. And in this case, there is a cost to this DDoS. We're just leading like to what we call friendly fire. Just because the resolvers get an answer, they increase the normal traffic up to 8.1 times, and that's called friendly fire. So this is not noticed during DDoS because it's a normal legitimate traffic. So if you're an operator and you over-provision your server by 10 times, you have to know that this particular scenario in here, you're gonna get 8 times more normal traffic because Recursive is gonna be trying to get an answer. So implications, caching works really well in retries, provided that some authoritative stays up and caches last longer than the DDoS. And one thing you can probably do is like make one very strong, because if you have one up, it's going to be fine. And this research explains prior root DDoS outcomes. And there's a trade-off between the TTL and DNS resilience. And many commercial websites have shorter TTLs. That also explains the pains of the dying customers and users' perception of the attack. So conclusions, the first study to evaluate is the resilience of the DNS from the point of view of the users during DDoS. Caches and retries working well. And there's a clear trade-off between TTL and DNS robustness. And serving state is kind of being controversial, but some deploy it, and it was the last resort. And that was not included in the paper, but that I would bring up to discuss here with the community. I think that's the best place to talk about it. So this is a graph I plotted to show that TTL of the records. I just chose Amazon.nl because they're CDN and they have a very short TTL as all the CDNs in the last record. But this is not in scale, this graph, but you can see the different levels of the DNS hierarchy have a different TTLs. So you see like the NS record of the roots are longer, shorter than the A, and .nl is the opposite. And Amazon is like the roots. And I'm trying to figure out, bring some reason. That's the thing I was asking Dwayne yesterday. I'm trying to make more science into how you set the TTLs. I can talk about .nl. We had a shorter TTL before than our NS because during the time when we had unicast, because if there were problems, we can quickly redirect the traffic somewhere else. But now we have all anycast, so it doesn't really matter that much anymore. I also found if your NS expires in somewhere else's caches, their A or quad A will also automatically expire. So having an A record longer than the NS, I don't think makes sense, or maybe I'm missing something. But the next thing I'm going to be doing is like how you set your TTLs correctly. And I think with that I conclude. Yeah, so that's a paper. Thanks all the people. And we call when the dikes breaks because this is a dike here in Holland. And if they break, we are going to be swimming because we're 2 meters below the sea level here now.
Tail, thank you very much for this research, which you had previously shared with the ServStale team in order to lend support to the idea that ServStale will help in extreme cases. The question that I had about it was, you considered successful client interaction just to be that a DNS response came back that wasn't ServFail, right?
That is correct. Okay answer, yeah.
So you didn't actually look at application behavior or actual end user behavior in the face of an answer that didn't come back fast enough, because some of your answers came back, but after 4.5 seconds. Yeah. And for many applications, that could in fact be equivalent to a failure. So.
That is correct. So we use as vantage points the RAP Atlas, and we set up the timeout for 5 seconds. So we didn't look in the applications. That's, yeah. But you're right, absolutely. Benno.
Benno Overein, Netherlands Labs. Thank you, Gio. So Unbound also did implement serve stale, or serve expired, it's called. We made our own relatively simple implementation, so we were not afraid of IPR. Tail can tell more about that. Mm-hmm. And of course, TTLs are being used. Sometimes they are not being used. We also learned from other DNS providers that they have their own rules, how long they keep their content in caches. And that if we do serve stale or serve expired, sometimes you have to clean your cache, because if it's signed data, if the signatures are expired, we have to flush them anyway. And the other thing you said, the resolvers would hammer the authorities because they try. There's also an option in Unbound to rate limit that.
All right.
So
thanks.
There are some tools here to reduce the DDoS from the resolver side.
All right. Okay. Yeah, so since we did not control the resolver infrastructure, I don't know even what resolvers, what they're running, I have no idea about that. But in the we also published a tech report, which is this paper with some appendixes. And I look into one probe, and what I found is that during DDoS, if they couldn't get an answer, they would activate more resolvers. So instead of only using 2, they would use 8, and they would hammer. So it's a very complex beast, this resolver thing.
Yeah. I don't know about the default settings for the rate limiting actually, but probably off. For stale, serve expired is off default.
Okay.
So.
Thanks. No, that's good. Good note. Yeah. Thanks.
It really, on the resolver side, I mean, some are hammering, but some are also would back off, because I know the algorithm that we have, we would back off if we do not get an answer, because we don't want to hammer the authority. The other thing that you need to maybe have a look at, you did a domain that was unpopular.
That's correct.
I guess that if you used a popular domain, the results would, or if you curate more often, the results would be different, because there's also something implemented in Resolver called prefetching. So when the TTL comes to the end, they will sort of go out and do that. And some implementations are also using that mechanism for the serve stale. And the other thing with serve stale is if you are unpopular, the LRU mechanism of the server will just kick you out because you're not popular. Whereas if you are popular, the probability that you're still in the LRU is much higher.
Yeah. Yeah, no, yeah, absolutely. So the thing with, since we are using RAP Atlas, we cannot send that many queries. So our design is like the lower bound. So at least we know with an unpopular domain what would happen. So with popular, we'd expect would be better. Yeah. But I mean, we look at our name servers at .nl for NS1, the DNS.nl, until NS4, and the cache in normal circumstances behave the same, like 30%, they're not cached as we expected. So even though our setup was a domain that we only use, but we also look at popular ones that we run. So we have both sides. But depends, I mean, I wouldn't know how it would be for a Google .nl because we don't run them, so it's hard to tell. But yeah.
Thanks.
Hi, Puneet from Google. Just a correction, Google doesn't do serve stale right now, but we are evaluating the serve stale draft for implementation in the future. And one other thing I'd like to point out for the client experience is that, especially for web browsing, you're not just resolving one name, you're resolving multiple names. And given the state of client libraries, if you're not using DO, something in the browser, it's mostly synchronous one after the other. So the user experience is even worse under attack, right? Because the queries are mostly happening serially one after the other.
All right. So, I mean, about the Google not doing so, I will talk to you about that offline maybe, because that's the IPs we saw doing. But thanks for your comment about the user experience. Yeah, that's a nice one. Yeah. Thanks.
Our next presenters are Vasson and Mohsen from AFNIC, and this presentation will not appear on the webcast.